Today's lecture is lecture 31, 10.3, and 10.5 to 10.6, and 10.10. So this will be covering our effect of intermolecular forces on liquids and solids and our types of solid bonding. So recall our last lecture where we introduced the idea of intermolecular forces. And so these intermolecular forces are the interactions between individual atoms or molecules that hold them together. So these forces are electrical in origin and result from the mutual attraction of unlike charges or the mutual repulsion of like charges. And so our four different types of intermolecular forces are our ion dipole interactions, and then our three different van der Waals forces are dipole-dipole, London dispersion, and hydrogen bonding. And so the more different types of intermolecular forces that you have, the stronger the interaction between your molecules that can hold it together in a solid or a liquid form. So intermolecular forces can either form between like molecules or between different molecules. So intermolecular forces that form between like molecules, which means of molecules that are the same identity, are responsible for the formation of liquids and solids. Okay, so we have the solids are held together and liquids are held together due to really strong, in the case of solids, or kind of moderate intermolecular forces that hold them together as into these sort of firm structures for the solid, or sort of a weakly held together structure for a liquid. Whereas in gases, we know there is little to no intermolecular forces interaction between gas particles. And so, but the intermolecular forces between different compounds have various effects. For example, if we take a look at the intermolecular force of water as it relates to ions in a salt crystal, that is responsible for solubility. So that is that ion dipole interaction of those water molecules, each with a dipole moment surrounding these ions in a salt, that causes that energetics to dissolve that solid in water. Other examples of intermolecular forces between different compounds are surface wettability and adhesive properties. So let's take a look at adhesive versus cohesive properties. So adhesive properties is defined as molecules preferentially sticking to other substances, whereas cohesive properties is that where molecules preferentially stick to like substances or to itself. And so examples that we have for adhesive and cohesive properties are shown here on this figure. So we know when we read a graduated cylinder, we observe a meniscus where the water is higher on the outside of the cylinder than it is on the middle. And that's because there is an adhesive property where these water molecules are preferentially sticking to the outside glass structure such that that water is sort of creeping up the sides and lower down in the middle. Whereas if we take a look at mercury, when it's in a glass structure, mercury is more cohesive, where the molecules preferentially stick to themselves rather than the glass. And you can see that we have this sort of inverse meniscus here, where you have a sort of mounding up of that mercury on the top. So these intermolecular forces that hold liquids together are responsible for two different factors, surface tension and viscosity. And so intermolecular forces within a liquid can be disrupted by converting that liquid to the gas by increasing the temperature. And we know that as the vapor pressure. And so we'll get into all three of these sort of ideas in the upcoming slides. So first off is surface tension. So surface tension is defined as the resistance of a liquid to spread out and increase its surface area. So we know by looking at nature that we can see these water bugs are able to stride along the top of the water without actually falling through. And you can actually see where each of their individual legs are touching the water. You see a dimpling in of the water, but it doesn't actually have enough force to pierce through and fall in. And we also see this in the case of water droplets, or in this case, mercury droplets, are being held together into these round droplet forms instead of evenly spreading out as a monolayer. And so, what is the reason for this surface tension to actually form? And so if we take a look at at water or a liquid that is in a vessel, or even you could say in a droplet like this, you can see that that liquid is made up of individual molecules. And so we know that there are intermolecular forces that are at play between each of our individual molecules. Whether those intermolecular forces are London dispersion, dipole-dipole, or hydrogen bonding, or any combination of those, you're going to see that there will be an attraction between each of our individual molecules. And so when you're talking about a molecule that's deep into solution, you're going to see that that attraction flows all the way around in 360 degrees. So molecules that are above, below, to the left, to the right, to the front and the back, all the way around in 300-degree angle. Whereas if we talk about molecules that are located on the top of a surface, we have we don't have any interactions with the top. We only see interactions for the right and left, and in the bottom and in and out, but none to the top. So what we get here, again, if we talk about summing together all of these vectors of intermolecular force interactions, we can see that our left and right forces are cancel each other out, but there's no net vector going upwards to cancel our vectors going downward. So what we have is a surface tension, where on the surface of a material, we have a net force pulling downward caused by the intermolecular forces between the surface molecules or surface atoms and all of those atoms or molecules that are located lower in the sample. And so this produces a tension where all of our surface molecules are being pulled downward. And so this produces the surface tension that allows a bug to stay on top of water or allows a sort of spherical droplets to form within a solution. The other topic that we can think of is viscosity. So viscosity is a measure of a liquid's resistance to flow. So we can see here that we apply this viscosity number. So when we're dealing with thick materials like glycerol or mercury, we see that we have a large viscosity. Whereas when we're talking about rather thin materials, so water, benzene, pentene, we're looking at very low viscosity. So the higher the viscosity, means the more resistance there is to current flow. So the thicker the material is a high viscosity. So honey is a very high viscosity. Water is a very low viscosity. Air is an even lower viscosity. Okay, any sort of fluid. So whether you're talking about liquid or gas, you can measure that with viscosity. Okay, so if we take a look at these viscosity values where we have our high viscosity to low viscosity, we're talking about different amounts of intermolecular forces. So the stronger our intermolecular forces, the higher the viscosity. The lower our intermolecular forces, the lower our viscosity. So now let's talk about our equilibrium existing between our liquid and gas phase that we know as the vapor pressure. So the vapor pressure is defined as the partial pressure of gas in equilibrium with liquid at constant temperature. So if we take a look at a solution of bromine here, we can see that bromine naturally is at a liquid state. But we can see and so it's a brown liquid, but we can observe this sort of brown gas that hovers above the liquid. And so this is due to an equilibrium between our liquid and gas phases. So if we think about whenever it rains outside, we can see that after a rainstorm, there are all of these puddles that form. Have you ever thought about why do these puddles evaporate? So we know that the boiling point of water is 100 degrees Celsius, okay, or 212 Fahrenheit. So the we know that when we increase the temperature to 100 degrees Celsius, that we're going to observe this boiling event, and boiling is our transfer between liquid and gas phase. But why do these puddles evaporate when we're not actually reaching 100 degrees Celsius? So it can be 60 degrees outside after it rains, and these puddles evaporate. So the reason is because there is an equilibrium between the liquid and gas phase that is temperature dependent. And this equilibrium we know as the vapor pressure. So if you think about a solution of water, so we have all of our different water molecules that are going to be in our liquid phase. And so those liquid molecules are going to be held together by our intermolecular forces that hold them together. And so that keeps it into a liquid and it forms our viscosity and also forms our surface tension at the top. So, but these water molecules are moving around in solution. And so as they're moving around in solution, there can be water molecules that have enough energy to escape out of liquid phase and now be H2O molecules in the gas phase. And so the higher the temperature that we have exposed to that water in the liquid phase, the faster all of these molecules are moving around within that liquid phase. So therefore, there's more molecules with enough energy that there's enough molecules that are moving around with enough energy to actually escape that liquid phase and transfer out into the gas phase. So this makes sense that when we're talking about in the summertime, when we're dealing with very high temperatures, the puddles on the ground evaporate very quickly. But when we're talking about in the fall or the winter, if we have a rain during these colder times, those puddles will stay there for a long, very long period of time because there's not as much energy for these molecules moving around in the liquid phase to escape to our gaseous vapor phase. Okay, so the vapor pressure talks about the temperature dependence of the equilibrium between liquid and gas. And so the puddle ends up evaporating because those gas molecules can just diffuse then out into the bulk all the way away. And then so that equilibrium, which exists right at the interface between the liquid and gas, never actually ends up reaching its total equilibrium because that gas phase keeps moving away. But if you held that water in a closed container, you would observe that the vapor pressure would be constant. Okay, so if we take a look at, excuse me, if we take a look at the vapor pressure, when we're looking at various different temperatures, and so this is the vapor pressure of water at various different temperatures, we can see that as that temperature goes up higher and higher and higher, that we can see that the vapor pressure goes larger and larger and larger. And so that makes sense because we're having more and more energy for that water to escape. All right, so with that, let's ask the question. Which of the following is true pertaining to the difference between bromine in the liquid and bromine in the vapor phase? A, the vapor molecules have weaker intermolecular forces than those in the liquid phase. B, the molecules in the vapor phase have enough kinetic energy to overcome the intermolecular forces. C, the vapor is composed of bromine atoms rather than Br2 and so have weaker dispersion forces. D, there's no difference in the vapor pressure in the liquid versus gaseous Br2, or E, none of the above. So pause the video and think about that. So the correct answer here is B. The molecules in the vapor phase have enough kinetic energy to overcome the intermolecular forces that hold them together in the liquid phase. So remember, once those Br2 molecules have enough energy to escape that liquid phase, there's no longer intermolecular forces holding them together. So next we're going to switch gears here and we're going to move on to discussion of our different kinds of solids. So what are the different forces that hold together different types of solids that we will encounter? So there's two main types of solids that we can talk about. One are amorphous solids and the other is crystalline solids. So amorphous solids are where the constituent particles are randomly arranged and have no ordered long-range structure. For example, rubber. Or we can talk about amorphous silicon glass. Okay, silicon dioxide glass here. So we can see that there's no ordered structure between the silicon and the two oxygens as they sort of orient within space within this glass. And then we know rubber too is also something that there's no sort of ordered crystalline structure. Whereas these crystalline solids are where the constituent particles have an ordered arrangement extending over a long range. And so here we can see quartz crystal. So same equation, silicon dioxide, but you can see that this quartz has a very highly ordered structure that actually extends to its macrostructure, whereas the amorphous glass does not. And so over here, amethyst here, we can see a lot of our fine rocks and minerals here carry a very crystalline ordered structure as well. And so within these crystalline solids, we have four different types of structures that we can discuss: the ionic solids, molecular solids, covalent network solids, and metallic solids. Okay, so attractive forces for solids versus liquids. So we've already stated that liquids are held together as a result of intermolecular forces. But crystalline solids are held together as a result of various attractive forces. So it's not just intermolecular forces, it could be several different things. And so the classification of our different types of crystalline solids depends on the type of force holding the solid together. So we'll see in the next few slides here that ionic solids are held together by Coulombic attraction. So that's that Coulomb's law, Q1 over Q2, or Q1 times Q2 over D squared. So we had that equation previously. We have molecular solids are held together by intermolecular forces. Covalent molecular solids are held together by covalent bonding. And metallic solids are held together by metallic bonding. So let's take a look at each. So ionic solids, we should be very familiar with these crystal lattices, where the particles are ions that are ordered in a regular three-dimensional arrangement and held together by Coulombic attraction. For example, we have sodium chloride. So we know this crystal lattice here for the ionic compound or ionic solid is held together by that Q1 times Q2 over D squared Coulomb's equation. So that's held together by Coulombic attraction, ionic solids. Next is a molecular solid, where the particles are molecules that are held together by intermolecular forces. So for example, we have ice. So solid water ice. So you can see we have this highly ordered structure of water molecules, and this ice is being held together by these hydrogen bonds that are located between our oxygen, hydrogen, and the lone pair on the neighboring oxygen. And if we take a look down this structure, we can see that it is crystalline in nature and that it's very highly ordered, but it's held together by these intermolecular forces. Whereas our ionic solid was held together by those Coulombic interactions, here we have our intermolecular forces holding the ice together. Next is our covalent network solid. So this is where particles or atoms linked together by covalent bonds into a giant three-dimensional array. So our example here would be looking at quartz. So for the quartz, if you recall back a few slides back as well, we have this crystalline quartz structure here, where all of these silicon and oxygen atoms are going to be covalently bonded to one another. So instead of being held together by Coulombic attraction for ionic solids or intermolecular forces for molecular solids, these covalent network solids are a giant structure that everything is held together by actual covalent bonds. So within this covalent structure, we have allotropes. So allotropes are defined as different structural forms of the same element. So if we take a look at elemental carbon, carbon can be present in several different forms. We could either have graphite, which has sort of planar sheets, and we know graphite from pencil lead. Or if you have it in more of a three-dimensional shape, so these flat sheets for the graphite, this is sp2 hybridized carbon atoms. But if we have sp3 hybridized carbon atoms, we form diamonds. So one, graphite, they're both carbon. It's exactly the same material. It's just sp2 versus sp3. So we know that graphite, pencil lead, we throw this graphite away and don't even think about it. But sp3 hybridized diamond, we fight wars over. So it makes you kind of think about the difference in the value that we place on certain items. It's really elementally the same thing. And another sort of allotrope that we can have for carbon is the Buckmeister fullerene, or also carbon nanotubes. So some of these, all of these are individually just carbon, but they're just different structures of these sort of covalent network solids. So finally, I'd like to introduce metallic solids. So metallic solids are where particles or metal atoms held together by metallic bonds, which are overlapping valence shells. And so this allows for excellent electrical conductivity. So for example, any of our transition metals, iron, copper, lead, any of these sort of metals, silver, gold, any of these metals are going to be held together through a metallic bond. Okay, so in that sort of case here, we have our individual metal sort of nuclei and core themselves, but the valence electrons kind of overlap with each other to form what we call a mobile electron sea that allows electrons to be able to transfer very efficiently through the material. So in summary, we have four different types of crystalline solids: our ionic, molecular, um, our covalent network, and our metallic solids. And so each of these are held together using a different type of attractive force. So ionic is held together by ion-ion Coulombic interactions. Molecular solids are held together using these intermolecular forces. Covalent network solids are held together by covalent bonds, and metallic solids are held together by metallic bonds. So each of these have slightly different properties to them, and we can see our examples of each one as well. All right, that's it for the day. Thank you.